Okay, so last time we were looking at I think that was last week. Okay, we are looking at the representation of sets on the number line, right? We're looking at the representation of sets on the number line. So if you missed that class, the video is there on Drive. You can watch it anywhere at any time. Okay, so today we want to look at the concept, okay, where we are proving set identities. Okay, so I'm pretty much sure you I taught about the basic rules or the basic identities that we have, okay, in math. I said we have the commutative rules, the associative, the distributive rule, and the De Morgan's law. Okay, so we want now to prove all those identities that we were stating. Okay, so we said the commutative laws, okay, they state that it doesn't matter the order that your set have, okay, they will still be equal. Okay, so if, for example, I have, let me say I have A, okay, if this A is intersecting B intersection C, okay, so this guy here will be the same as, okay, I'm writing, this is distributive, right? Okay, it will be the same as A intersection B and then intersection C, okay? So it doesn't matter the order with what you start with there, it will just be the same. So meaning if I use my commutative laws, it will be A intersection B is the same as C intersection B, okay? Doesn't matter the one that you start with here. Okay, you can start with this, or you can start with the set C. Your answer is going to be the same, okay? And then I also talked about what we call as the De Morgan's laws, okay? And these laws are very important because you're going to be examined on them, okay, whether you like it or not. So we said for the De Morgan's laws, if I have A, this is just a recap, if I have A union B, okay, and then I take the complement of this set that we have here is the same as if I have A complement, then I'm intersecting it with B complement like that. So whatever elements that are going to be in that set, they will be the same members that will be in this set. Okay, so this was the first De Morgan's law. And then we said we had two, so which means the other one would be A intersection B. Our complement is the same as A complement union B complement. Okay, so in today's class now, we want to prove that really this guy here is actually equal to this, and that guy is actually equal to that. Okay, so that's what we mean when we say we are proving the set identities. Okay, so we have two ways in which we prove the set identities. Okay, so we have two ways. So let me write here. We have two ways in which we prove the set identities. Okay, so we have a lot of set identities, but you just have to get the concept, then you'll be able to solve in. So we have basically two. Okay, they can be more, but the most important for you guys not taking NS and premates, you can say we have two. Okay, so these two methods, the first one is what we call as the elementary method. Okay, the elementary element. Okay, so yeah, I'm supposed to put in elementary. Okay, membership method. Okay, so elementary membership method. This will be the first method that we'll use. So in this method, you will be given sets, and then you are going to use those sets, the members in those sets, to prove the identities. Okay. So if you're not given and then you are asked to use the elementary membership method, okay, it means you can just come up with your own sets and then you prove that identity that you've been given. So this is the first method, okay, where there is listing of members in that specific set. And then the other one, okay, the other one is what we call as okay, the other one is what we call as the abstract method. Abstract. Okay, so in this method, we assume that a certain element is a member of a certain set, and then we also want to show that that same element is a member of the other set. Okay, so maybe you may not understand what I'm trying to explain, but with the examples, you're going to understand. Okay, so we have two, I said elementary, and then we have the abstract what? Method. Okay, so I'll pick one identity, and then we are going to prove it both ways. We are going to prove it using the elementary membership method, and then we are also going to prove it using the abstract method. Okay, so for example, let's prove that A, okay, union B, complement is actually equal to A complement intersection B complement. Okay, so let's prove this using both methods. So we start with the elementary membership, and then we go to the abstract. Okay, so I said in the elementary membership, you have to come up with your own sets if you're not given. Okay, you have to come up with your own sets. So let's say I have my universal set here as 1, 2, 3, 4, 5, 6, 7. Okay, let's say this here is my universal set. Okay, and then I say my set A will just be let's say 2, 5, and then I have 7. Okay, and then let's say my set B contains the following. Okay, so let's say my set B has 6. Okay, let me start with a lower number there. Let us say that my set B has 1, and then it has 6 there. Okay, so let's say this is my set A here, and then this is my set B. Okay, how are we going to prove that the A union B complement is actually equals to A complement intersection B complement? Okay, so we just want to find the members that will be in this set, and then see if those same members are in that set. That's what we are going to do here. Okay, so if you have any questions, just unmute yourself, and then you're free to ask. You're free to ask. Okay, so let's do that. So let's start by finding the members that are in that set. Okay, the set that we have on our left hand side. Okay, so on my left hand side, I have the set A union B. Okay, I have A union B, and then I have a complement outside there. So how can I find the members that are in A union B complement? It means I have first to find the members that are in A union B. Okay, so A union B, we said it's just combining the sets A and B. So we are going to say A union B is equals to, okay. So let's combine these members here, starting with the lowest. So the lowest there will just be 1, and then we go to the 2, and then we go to the 5, then we go to the 6, and then we go to the 7. Okay, so this here will be my A union B members. Okay, but remember that my interest is in the A union B complement. So meaning I have to find elements that are not in this set. They are the ones that are going to sit in that set. So I'm going to say A union B complement, okay, will be all the members that are not in this set, but they are present in the universal set that we chose. Okay, so what was our universal set here? Our universal set was 1 to 7 there. And then if I look at my A union B, I see 1, 2, 5, 6, 7. Okay, so meaning all the elements that are not in here, but they are in the universal set. So I can see that we don't have a 3 here. So my 3 will sit in the complement, and then even my 4 will sit in the complement there. Okay, So it means my set A union B complement is just 3 and 4. Okay, so these are the members in my A union B. So we want again to show that these same members will be in the set A complement intersection what? B complement. Okay, but before we solve this, any questions here? Are we okay? Or I've lost you somewhere, or we are following? Hello? Hello, guys. Are we following? I need feedback from you guys. Okay, someone has said yes, yes. Okay, so let's, okay, so we've shown the members of the set A union what? B complement. Now we want to show the members that will belong in this set A complement intersection B and see if they are going to be the same element, okay? So if we find the same element in this set, then it will mean that our proof is done. Okay, so let's go there and find. Okay, so we now want to find the members of A complement intersection B complement. Okay, so someone is writing on my screen. I don't know why. Okay, let me switch these off. Let me switch the annotations off. Okay, disable annotations. Okay, that's better. So now I want to find the elements that are in here. Okay, so as usual, we first have to know the elements that are in the A complement. Okay, so the A, what members did it have? So we can check here. The A had it had 2, 5, and 7, and then the B had 1 and 6. Okay, so the A is 2, 5, and 7, and then the B just had it had 1 and 6. Okay, so meaning A complement are just all those members that are not in A, but they are in the universal set. And our universal set was from 1 to 7. So whatever numbers I cannot see here, I'm going to put them in the A complement. So meaning 1, the 3, the 4, the 6. Okay, these elements are going to be in my A complement. And then let's find for the B complement. Okay, so all the numbers that I cannot see here from 1 up to 7, they'll be in the B complement. So meaning 2 could be there. 3 will be there. Even the 4 will be there. And then the 5, the 6 is there, so meaning the 7. Okay, so this is what we have as our what? Our B complement. So now let's find the intersection of this A complement here and this B complement there. So we are going to say A complement intersection B complement. Okay, we know that the intersection takes the common elements that are in A complement and B complement. So what elements are common between these two sets? Okay, so we can see that the 3 is common. And then what else? We can see that the 4 is common again. Okay, so this is my set A complement intersection B complement. Okay, so now we compare this set here to the set that we found by the first, which was the A union B what? Complement. So what members did we have in the A union B complement? So we can check here. We had the 3, 4. Even in this set, the A complement intersection B complement, we still have the 3 and 4. So what does that mean if two sets contain the same members? It means they are equal, and we would have proved our identity. Okay, so here you can conclude. You say since my A union B, okay, my A union B complement is equal to my A complement intersection B complement, which is equal to the members that we have, which was the 3 and the 4 there. Okay, since we have this situation, then definitely my identity, which is A union B complement, will be equals to A complement intersection B complement. Okay, so here you can write hence proved. Hence proved. You would have proved the identity. Okay, so anyone have lost here, or we are following? I can now prove it using the abstract method. Okay. Are we following, guys? Okay.
Sir, me, I'm a bit confused. I don't know why you contributed the numbers which are reflecting in the A complement. So you're saying that the A complement is 3. I don't know. And also in the B.
Can you come again? I didn't get what you say. What are you asking me? You are saying?
Oh, you're saying the answer, the A intersection B complement means that the 3 and 4 are common, but there is a sign of a complement, meaning that these two they are not supposed to show. I don't know if I'm confusing myself.
Okay, so I don't think you are confusing yourself, but you're just, the concept has not yet sunk in, okay? So if you're talking about this guy here, okay? So the complement there means the elements that are common with the first set that you write and the second set that you write, right? So here when we are finding, where was this? Okay, so here when we are finding, this here on top was our set A, and that was our set B, okay? And we want to find A complement intersection B complement. So what did we do? We first had to find the A complement, okay? The set A complement, and we also found the set B complement here. So these were the members that we found in the set A complement. Okay. And then these were the members that we found in the set B complement. And then now we want to get the common elements between this set and this set. No wonder we ended up with the 3 and the 4 there. You've gotten it now? Okay.
I'm clear now because I didn't see the top part.
Okay, yeah.
Yes.
Okay, so that's that. Okay, so I can see in the comment someone saying this is the De Morgan's law. Yes, so this is the first De Morgan's law that we are proving there. That's the first De Morgan's law. Okay, so this method that we were using here is what we call as the elementary membership method, okay, where you show the specific members that are in that set for you to prove, okay? And then now we want to prove the same identity, but using what we call as the abstract method, okay? Okay, so this is what we are proving. We have proved it using the elementary membership method. Now we want to use the abstract method, okay? The one that does not involve listing any set members. Okay, so a question can come. Okay, so a question can come, they're saying proof. I'll use the same identity so that we see that any method can work. So complement is equals to A complement intersection what? B complement. Okay, so I want now to use what we call as the abstract method. So in the abstract method, we just assume that a certain element, okay, that will be a single element, that a certain single element is a member of this set, okay? And then we want to prove that that same element is also present in this set. Okay, so when I was talking about the set operations in the other lesson, I said for you to consider two sets to be equal, okay, then it means they have to be subsets of each other. So if we claim that the A, if my set A is equals to set B, then under set theory, it means that A should be a subset of E and B should be a subset of what? A. Okay, so this is what we mean here. If A is equals to B, then A is a subset of B and B is a subset of A. Okay, so in this abstract method that I'm talking about, okay, we just want to prove that what we have on the left-hand side, okay, that we have here on the left-hand side, we want to prove that this guy here is a subset of this guy. And then again, prove that this guy here is a subset of that guy, okay? Okay, so let's do that. So how do you do that? You suppose, okay? So you say proof here, okay? You underline, and then you say suppose, okay? Suppose that I have X being a member of what? Of this set that I have, which is A union B complement, okay? So suppose that X is a member of A union B complement, okay? Then what does this mean? Okay, so I'll give a simple example. So if you are inside the house, it means you are not outside the house, right? Okay, so if you are seated inside your house, the way you are, or your boarding house, I don't know. If you are seated in that house, it means you are not outside that house. And then if you go outside, it means you are not inside that house, okay? So we're going to use the same logic in the set theory form now. So if X is a member of A union B complement, okay, then it means this X, the same X, is not a member of A union B, okay? Because this X is in the complement. So it means in the actual set, it's not there, okay? So if I confuse you, just let me know, right? Okay, so if X is a member of A union B complement, then it means that X is not a member of A union B. Okay. Okay, and then what's the next step from here? So if X is not a member of, let me put it in the brackets. So if X is not a member of A union B there, we can actually expand this and say that the X is not a member of A, okay? And then we are saying union here. So the union in words, it means or, okay? And then the intersection, it means and. So if I have union there, I'm going to say X is not a member of A, or, so this or here is this union that I've put there, okay? Then I'm going to say X is not a member of B. Okay, so this is what I will have there. I hope you're following. If you're not, please don't hesitate to ask. So if X, okay, if X is not a member of A, then it means what? It means that X is a member of A complement. Okay, so if X is not a member of A, then it means that this X is a member of A complement. Okay, and then immediately here you change from this not a member of to a member of. It means this or here has to change from or, it becomes and. Okay, becomes and there. And then here we are going to do the same thing that we did there. We're going to say X. Since X is not a member of B, it means that the X is a member of what? B complement. Okay, so the situation that we have there is that this X is a member of A complement, and that same X is a member of that B complement. Okay, so what does that mean? It means that X is a member of A complement, okay? And then this, we said in symbol form, the and is just the intersection, and then it's also a member of what? B complement. Okay, so I don't know if you've seen what we've done there, okay? So we started with what we had on the left, okay, which was the union, A union B complement, okay? We said this X was in that set. And then at the very end, we can see that this X is still in the set that we have on the right-hand side. Okay, so we started with this assumption here. Let me use white here. We started with this assumption here. We assumed that this X was in the A union B complement, right? Which is this expression that I have on the right. And then after manipulating it, we are finding that this X is also a member of A complement intersection B complement. And this guy here is what we have, on the right-hand side here, you see? So if X is a member of this, and then again, that X is a member of this, okay? then it means that this guy is a subset of this. Okay, so this you would have completed the 50% of the proof. So you are going to say A union B complement is actually a subset of this guy here, which is A complement intersection B complement. Okay, so this here will be 50% of the job. So you can label this as my number one equation, or you can say this is my equation one. And then now you go to the next step where you are going to show that this A complement intersection B complement is also a subset of this. So if we achieve that, then we can say that the two sets are what? Are equal. So, okay, so let's do that. So if I can go that, make that disappear. Remember, we are proving this, right? So don't get confused. And then there we have A complement intersection B complement. Okay, so now we want to prove that if I have an X here, that X can end up in this set. Okay, so I'm going to say proof. Okay, proof. Okay, so I'm going to say suppose I have an element X, which is a member of this set that I have on the right there. Okay, complement intersection B complement. Okay, so if I have A X being a member of this, okay, what does that mean? It means that I can expand this. I can say X is a member of A complement, okay? And then this intersection here becomes and X is a member of what? B complement. Okay, and then from here, I can see that if X is in the A complement, what does that mean? It means that the X is not a member of what? A, okay? And then on the other side there, X will not be a member of what? Okay, X will not be a member of B. Okay, so here the X was a member of A complement. It means that this A, okay, this X, I mean, is not a member of A. And then on the other side, I had X, which is a member of B complement. So it means that that X is not a member of what? B. Okay, so any questions there? Any questions there? Have I confused anyone before I continue? Have I confused anyone? I can continue. Okay, okay, let's continue. Let's continue. Okay, just a minute. Okay, so from here we see that okay, I see some questions. Yes. Okay. Okay, and then from here we see that if X is not a member of this, or it's not a member of this. Oh, here I forgot. Okay, so when you change this sign here, it means this word here from and it changes to O. Okay, so if A is not a member of, if X is not a member of A, and if that X is not a member of B, then it means that what? It means that X is not a member, okay, of A, and then this O here becomes the union, and then I have B. Okay, so X is not a member of A union B. So if X is not a member of A union B, then it means that the X is actually a member of what? Of A union B complement. Okay, so if the X is not a member of A union B, then it means that the X is a member of A union what? B complement. Okay, so this is what we have there. Okay, so we can see that we started with what we had on the left, on the right-hand side, and then we are ending up with what we had on the right. Okay, so initially, then let me change the color. So initially, we had an X that was present in the A complement intersection B complement. But right now, when you go down, we see that this X is present in the A union B what complement. Okay, so meaning that the A complement intersection B complement is a subset of this guy, which is A union B complement. Okay, so since we found that this, okay, so we can say this is our equation 2. So remember, in the equation 1, we said this guy was a subset of this. And then in this equation 2, we are saying this guy is a subset of this. So if we have two sides of the set and they are both subsets of each other, we can conclude that those sets are equal. And our proof will be what? Will be complete. Okay. So here you can say combining in your conclusion. Okay, you can say combining my equation 1 and 2. Okay, I get, or we get that. Okay, we get that A union B complement is actually equals to A complement intersection B complement, like that. Okay, then you can even write that hence proved. Okay, you write your hence proved. Yeah, it feels nice to write hence proved when you've done the correct thing. Okay, so that's how you prove. So we've shown two methods, so now we can prove that, right? We showed how we can prove it using that method where we are listing each and every element. And then we also use this abstract method where we're just showing one single element. So do we have any questions there? Do we have any questions? Okay, no questions. Okay, so let's look at another question. Let's look at another question. So let's prove this using the elementary membership method, where we have to list all the sets. Okay, so the question is saying, assume any arbitrary countable sets and verify the following. Okay, so the first one here that we want to verify is that A union B intersection C, okay, is actually equals to A union B, and then we say intersection A union C. Okay, so we want to prove that this set that we have here is actually equals to this set that we have here. And then they've told us to use the elementary membership method, where we have to list each and every member of this. Okay, so we can assume our universal set to be okay. So you can assume any set that you want. Okay, so let's say our universal set is 1, 2, 3, all the way up to 10. Okay, so this is our universal set. And then let's say my set A is 2, 7. Okay, and then let's say my set B will be okay, so let's say my set B will be 1, 3, 4. This is my set B, and then my set C. Let my set C be, okay, let's have 3, 5. Then we have 6. Okay, so let these 3 sets here, in fact 4 sets, be what we choose to be our sets. Okay, so remember you come up with this, so you can come up with any sets of your choice, because you're just trying to prove. Okay, so we want to show that the member that will be in this set, okay, will be the exact member that will be in that set. Okay, so let's get the first set there and see if we can find the member that it contains. Okay, so there we have A union B intersection C. So it would be wise to first find the B intersection C, and then you unionize it with the members in A. So, okay, so let's find B intersection C here. So what would be my B intersection C? So we check for the members that are common in this set B and that set C. So if we see there, we can see that 3 is common, so we put 3 there, okay? Okay, so in B intersection C, we only have 3, and then we are unionizing this B intersection C with the set A. And remember the union, it means we are getting all the sets, or all the elements in those two sets, right? So we are getting all the elements in set A and all the elements in this B intersection C, okay? So we are going to say A intersection B. Okay, this is union. Why am I writing intersection? Okay, we're going to say A union B intersection C is actually equals to, okay, and then with this, all the members are in these two sets. So set A has 1, 2, and then this one has 3. So we list them in order, so it will be 2, 3, and 7. Okay, so this will be my element in the set A union B intersection C. Okay, so now I want to see that if I find members that are in this set that I have here, will it be the same members that I have in this set? Okay, so in the other set is A union B, and then we are saying we unionize this. I mean, we intersect this with A union C. Okay, so here the first thing is to find A union B, and then to also find A union C. And then once we have those two sets, we can unionize them. Okay, so what is my A union B? Okay. So my A union B will be what? So we are just combining all the elements in set A and all the elements in set B. So if I can go back here to view my sets, in B we have 1, 3, 4. And then in A we have 2, 7. So it means in A union B, we're just going to have 1, 2, 3, 4, 7. Okay. So A union B, we're going to have 1, 2, 3, 4, and then I have 7 there. This will be my A union B. And then what will be my A union C? Okay, so my A union C, I have to write C here. So my A union C, okay, my A union C there, what is it going to be? Okay, so let's look at the set that we have here, the A and the C. So in the A, I have 2 and 7, and then in the C, I have 3, 7, 6. So it means in the A union C, I'm going to have 2, 3, 5, 6, 7. Okay. Okay, so saying 2, 3, 5, 6, 7. Okay, so this is my my A union C. Okay, and then now let's take the intersection between these two sets that we have here. Okay, so it means my intersection will be, I can write A union B. I say intersection A union C. Okay, and then we're just going to get members that are common in both these members. So what is common in these two sets? We can see that we have a 2 there and a 2 there. So I'm going to write 2 here. Then we have a 3, we have a 3. I'm going to write 3. Then we have a 7, we also have a 7 there. I'm going to write 7. Okay, so this will be my set for this set here. So we can see that what we had on the left and what we have on the right, they contain the same elements. Okay, because even the previous one, this one here, it also contained 2, 3, and 7. Even this one here, it has contained 2, 3, and 7. Okay, so what does this mean? It means that my A union B intersection C, okay, is actually equals to this set that we have, which is A union B intersection A union C. Okay, so since we are able to prove that they contain the same numbers, we can say hence proved. Okay, so any questions on that? Any questions on that? Okay, silence means people have heard. Okay, so if there are no questions, I think I'll end there, but I'm going to give you a question to solve. Okay, so please solve this question and then send your solutions to my inbox. I want to see if people have understood what I was saying. Okay, so I'm going to give you the other De Morgan's law to prove by the arbitrary method. Okay, so I want you to prove that A intersection B, and then I have a complement outside, is actually equals to A complement union B complement. Okay, so I want you to prove this. So you can screenshot. Okay, you can screenshot on your phone. And then once you find the solution, make sure you send it to me so that I can correct you. Okay, so you can prove that as a homework of the sort. Okay, so do I have any other question before I close the class? Okay, someone is saying they have a question. You can ask. Oh, that was a long time. Okay, so someone said, what method should we use? I said you use the arbitrary method. Okay, arbitrary. I don't know if there's an R there, arbitrary method. So that method that we used when we did the second part, where we said X is a member of this, and then we want to show that that same X is a member of this. That's the method I want you to use, not the one for listing the elements. Okay. Okay, so have a blessed night, and for any questions, my inbox is always open.